Okay, Chemical Reactions and Balancing Part 5. This is Chemistry Unit 8, Ms. Howard's chemistry class. We're really heavily focused on C8D to use the law of conservation of mass to write and balance equations. But we're still covering all these other ones also. So letter C, we're still talking about types of reactions. We did a synthesis reaction where you have two simpler substances combined into one more complex substance. And within that, we talked about combustion reactions. We did decomposition reactions, where it's just the opposite of synthesis. You take one complex substance and break it apart into two or more simpler substances. And now we're ready for letter C, single replacement reactions. Okay? Single replacement reactions are where one substance takes the place of another in a compound. So they replace one thing. Yeah? So you have A plus BX, and notice that the A stuff boots the B out of the way and takes its place. So single replacement reactions. Now, single replacement reactions, again, where you have one substance that replaces another in a compound, and typically it happens because it requires less energy, or the compound that's produced has less potential energy than the compound that was originally there. Okay, what do I mean by that? Nature favors substances with less stored energy within them. They're more stable that way. That's just one of those things that happens. So how do we know if A is going to kick B out of the way? We look on a chart. You have it on your yellow pages. It's called the activity series. If A is more reactive by itself than B, it'll boot B out of the way, and so it becomes more stable that way. B is by itself. B is a little bit less stable, but there was less potential energy in it than A was by itself. Blah, 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 right? We'll talk about this more a little bit later. So one substance replaces another in a chemical, in the compound. Whew, that took a while. Okay, there are two major types of single replacement reactions. First, you have a metal in a compound that is replaced by a more active metal, and that's where we use the activity series that's on your star reference materials or your yellow pages. So here we have an example. I'm going to try my spiffy pen again. Let's see if it will. Oh, there it is. Yay. So let's tell it to make a pen. Woo! And here we have aluminum plus, what is this compound? Name the first element. Name the second element. And this isn't just an element. It's a polyatomic ion, so name the polyatomic ion. Now, notice that lead is one of those weird ones that has more than one oxidation number. So in this case, we'd have to name it lead 2 nitrate. And how did I get the 2 in the name? Because I did the backwards crisscross method, and that plus 2 was the oxidation number for the lead. So we have aluminum plus lead nitrate, or lead 2 nitrate. And notice that the aluminum boots the lead out of the way and takes its place. So now we have pure lead plus this aluminum nitrate stuff. Is the equation balanced? Okay, so get a pencil, and you're going to balance this equation. So let's see, we start off with the metals. I have one aluminum on the left side of the arrow, one aluminum on the right. And if it makes you happy, you can just mark a line down the center. So we have 1 and 1. We're good there. We have lead 1 and 1, so looks like everything's great there. Then we look at the nitrate. Let's not take the N and the O apart. This nitrate, NO3, stays together on both sides. So let's just look and see how many of those chunks we have. Here on the left, we have 2 of the nitrate chunks. Over here, we have 3 of the nitrate chunks. Can I just cross this off and change that to a 3? No, because that changes the identity of the substance, and we can't do that. We can only balance equations by adding the coefficients. So if I have 2 of these nitrates here and 3 over here, I need to know what is their least common multiple. Like in math class, 2 times 3 is 6, right? So 2 times 3 is 6. That means over here, 3 times 2 is 6. So the nitrates, I have 6 of those nitrates on this side, and I have 6 of the nitrates on this side. Look what it did to my aluminum. I have 2 aluminums on this side, 2 of them, so I need to make 2 over here. So I'm going to change this to a 2, and now I have 2 aluminums on this side. Check the lead. I have 3 leads over here. And how many leads do I have over here? Oh, only 1. So change this to a 3. So now I have 3 leads. So 3 leads, 3 leads. 6 nitrates, 6 nitrates. 2 aluminums, 2 aluminums. Yay! Oops. Let's go down here and see if it'll let me. I don't even know. Let's go and change this from a pen to an arrow. Oh, look, there you go. Half of the hydrogen, here's another one. So we have 2 types of single replacement reactions, right? One, we have a metal is replaced by a more active metal, and the other one is kind of a weird one. We have half the hydrogen in water is replaced by a metal. So here's the metal, and the metal's going to boot the hydrogen out of the way, not all of it, but half of it. So we have Na and the O and one of the H's, right? Yeah, half of the H's. And then we have hydrogen gas by itself. So we've taken the sodium, booted some of the hydrogen out, so we have NaOH, and then we have pure hydrogen all by itself, right? Now we have to worry about balancing the equation, okay? So let's start off with sodium. Our sodiums are good, yeah? And our oxygen, there's one oxygen, there's one oxygen. On the left there are 2 hydrogens, and there are 2 plus 1 more. Oh, there we go. So let me change this back to a pen. I should get the eraser and erase that, but you know, that's just too much. Alright, so my hydrogens are the problem, right? I have an even number on this side. Again, I can just draw a little line down the middle. I have an even number over here and an odd number over here. And the only way I'm going to fix that is to make this side even too. So I'm going to start off, and I'm going to say, okay, let's try this. Let's put a 2 here. And that makes my numbers of hydrogens even, right? There are 2 hydrogens plus 2 more. Now I've got 4 H's on this side, right? 4 H's. And then over here I only have 2. So if I put a 2 right here, now I have 4 H's. I'm slanting here. My pen's going crazy on me. 4 H's on this side. Okay, so my H's are good, but I changed my O's, didn't I? I have 2 O's, 2 O's, so 2 O's and 2 O's. Yeah. Now all I have to do is look at my N's. I have my NA's, sorry. I have 2 NA's, 2 sodiums, and then over here I must have 2 sodiums, so I have 2 Na and 2 Na. And there we have it balanced. Okay, next one, hydrogen is replaced by a metal in an acid. And I think I might have only said 2, but there should be 3. Hydrogen is replaced by a metal in an acid. So remember, acids start with H. So we're going to boot that H out of the way and stick a metal in front of it. So sure enough, look at this. We have magnesium, and what acid is added to that? HCl. What acid do you know that has the Cl, the chlorine in it? Hydrochloric acid. So magnesium plus hydrochloric acid. And you boot the H out of the way and stick the Mg in there. You have to write the correct formula. So Mg has a +2 oxidation number. Cl has a -1. Do the crisscross method, and you get MgCl2. We'll practice these in class. So we get magnesium chloride, and then we dumped off the hydrogen that's over there by itself. You guys take a minute and make sure that you balance this equation. A halogen in a compound. What's a halogen? Halogen. Look at group 17. Group 17 are the halogens. A halogen is a compound. In a compound is replaced by a more active halogen. So it's like the Cl might replace the Br or vice versa. So again, usually those are listed on your activity series too. So here we have chlorine gas, and we add it to potassium. Name the first element, name the second element, follow what changed the ending to IDE, so potassium bromide. And the halogens are going to replace each other. All the other ones, it's been the first element, the cation is positive. Had to think about that one a minute. And the positive ones are usually replaced. No. But in this case, we have the negative ones that are replaced. So the chlorine bumps out the bromine. Notice chlorine and bromine on the periodic table are in the same family, so it works nicely that way. And number 3, the activity series. Thank you. The activity series. The activity series is what you find on your star pages. It's on your yellow pages. And it's a way to rank the elements, mostly metals, but usually they have hydrogen in there and maybe a couple of the halogens. And they rank them in order from most reactive to least reactive. And the most reactive ones will always replace the least reactive ones in a compound. So, excuse me, if two compounds combine, the most active metal ion will rearrange to form a compound with the most active non-metal ion. So the most active ones get together. Okay. If the two reactants are already in this state, then there isn't going to be a reaction that occurs. Okay, so that's the way you can tell. You use that activity series, and you can kind of tell if I put these two things together, is anything going to happen at all? The activity chart, again, is on your star reference pages. It's on your yellow pages. Your yellow pages are your star reference pages. They'll just be pretty white when you take the star test. Okay, next type of reaction is called a double replacement reaction. So we had a single replacement reaction where one thing took the place of another one thing in a compound. Here, they're actually going to swap. Two things are going to swap places. Okay, so notice the A and the B. They swap places. So now B is with X and A is with Y. Double replacement. To tell whether or not what type of reaction you've got, a lot of times, if you look at double replacement, they're typically going to be the ones that are in solution. They're usually the ones that are aqueous or aqueous. They're in solution. So we have ions of two compounds in solution are going to change places. One of the compounds formed is usually a substance that leaves the reaction environment. It either is going to bubble out as a gas, or it's going to form a precipitate and be that solid sludge that goes down to the bottom. So, or maybe it even forms water. But you have some type of substance that's going to leave the reaction environment. Okay. The other compound is usually soluble, and it remains in solution. So you could actually do a double replacement reaction, and if you filter off the liquid, and just so you get the precipitate, you could have one compound there, and then how do you get rid of the water for the other one? You evaporate or heat the water off, and then you've got the other compound that's left over. So you can actually get the two compounds once you get rid of the water. Okay, so here's an example. We have NaCl, which you already know what that is, plus AgNO3. So Ag, name the first element. NO3 is a polyatomic ion, name the polyatomic ion. So we have sodium chloride plus silver nitrate. And notice they're both aqueous. They've got that AQ beside them. That means they're both dissolved in water already. And it's going to produce two things. It'll produce NaNO3, sodium nitrate, plus AgCl. Okay. How do you know which one is the solid one and which one was still left in the water? That's when you look on another chart that's on your star pages. You have this solubility chart on your star pages, on your yellow pages, and that's how you determine is sodium nitrate the solid stuff, the precipitate, or is silver chloride the precipitate. If you take out your yellow pages, pause this, go take out your yellow pages. This is really important. You need to know how to use these charts. All right. You have your yellow pages, look at the solubility chart, and you notice that it says nitrates are soluble, and anything with a group 1 metal, the alkali metals, are always soluble. It's the silver, you got to look out for that silver. Silver chloride is insoluble, okay? And we'll go over this and use these charts in class too. Okay, so look at the next one. We have FeS. Name the first element, then name the second element, yes? Change the ending to IDE. So we have iron sulfide. In this case, it's iron 2 sulfide. We'll talk about how that is in class. And, oh, look, we bonded it to that HCl, or we're adding it to HCl, which is hydrochloric acid. And we produce H2S and FeCl2. How do you know which one is the precipitate and which one is not soluble in the water? Look on your solubility chart and find out. Circle the one that is the precipitate, or the one that is leaving the reaction environment. And then balance the equation. Pause this, balance the equation, and look at your chart. Did I say pause this? Go do this now. Okay. Notice again, there are the teaks. We're still going over. They're never